Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 2, Differentiation, the definition and basic derivative rules. Today's topic is 2.6, derivative rules, the constant, sum, difference, and constant multiple rules. Enjoy! All right, for 2.6, we're talking about some rules of derivatives today. Specifically, we're focusing on the constant rule, constant multiple rule, and sum and difference rules, which are going to help us take some derivatives of functions. We started last lesson talking about the power rule, and so that can only get us so far. We need to sort of think about what happens when we have coefficients or more complicated functions, and so these rules are going to allow us to do that. And today's notes is going to sort of be a grab bag of different skills. We've got a bunch of different topics that we're going to go through, but they're all sort of related and sort of like unlocked by these derivative rules, which we're about to learn about. All right, let's start with this first one. So derivative rules that are super important. We have this rule that's called the constant rule. So the derivative of a constant, right? Remember, constant is just a number, right? Like a number, not a variable. So the derivative of any constant is 0. Why? Well, let's think about a function. Let's say we've got the function like y equals 5. If we've got the function like y equals 5, we know that y equals 5 is simply a horizontal line. And we also know that the derivative, right, that d dx, is finding the slope of that line. Since this line is horizontal, right, and any constant function is horizontal, the slope of that line is going to be 0, right? It's neither going up or down as it moves to the right. So the derivative of any constant is 0. Be careful in these types of problems and these types of problems on like the AP exam and in multiple choice and in quizzes and tests like to try to challenge you with this rule. You know, this rule works even if a function is like y equals pi or y equals e, simply because both pi and e are numbers, right? We know pi is like close to 3.14. We know that e is like 2.718. In those cases, you know, these are actual numbers. We don't want to confuse them with variables. And so if I were to take the derivative of either of these, the derivative is going to still be 0. The derivative here is going to still be 0 because those are both constants. So just because it's not like a regular number, don't assume that you know, the constant rule doesn't apply. You need to think about what you're taking the derivative of. And if it's still a constant, that derivative is going to be 0 since the graph of that line will be horizontal. Next, so we did constant. Next we have this what's called a constant multiple. So I have the derivative with respect to x of some c value times a function u. So I'm going to call u, like we're going to say that u here is some function that we don't know. So u is a function, but c is a constant. So that's sort of also important that c is a constant. What is this? Well, so the derivative of this is going to be equal to whatever the c value is times the derivative of u. So I'm going to call that the derivative of u with respect to x. So du dx. Notice that the constant just sort of stays outside and it multiplies by the derivative of the function part. A really easy example of this would be to take a look at, like, let's say y is equal to 5x to the 10th power. 5x to the 10th power. If I take the derivative of that, we know that the derivative of the x to the 10th part from using the power rule is 10 times x to the 9th. What happens with that 5 though? The 5 just multiplies by that function, so the derivative here is going to be equal to 5 times 10, which is 50 x to the 9th power. So essentially what happens is we take the derivative of the function part and then just multiply the constant on afterwards. So that 5 just sort of hangs out outside while we take the derivative of x to the 10th, and then we multiply those together to get our final answer for that derivative. Nice. What about the sum or difference? This is a nice one because this allows us to do derivatives of functions with multiple terms, things that are being added or subtracted together. All this is it's going to be the derivative of u with respect to x, plus or minus, whether it's adding or subtracting, it depends, the derivative of v with respect to x. So all this is saying is that if I have more than one term that are being added or subtracted, just take the derivative of each part and then add or subtract those pieces. Great. So those are going to be our derivative rules for today. Let's try these out. We've got that y is equal to 2x squared minus 5 over x plus 6. Similar to our last lesson, I would encourage you, if this is not written as with exponents, to rewrite this so we can use the power rule. So 2x squared is fine, but that negative 5 over x, we know we can rewrite that as negative 5 times x to the negative 1 power plus the 6 that's on the end. All right, well, let's take the derivative of each part. So our sum and difference rule allows us now to take the derivative of 2x squared and the derivative of the 5 times x to the negative 1 and the derivative of 6, and then either subtract or add based on what's there. We know that from the power rule, the derivative of 2x squared is 4x to the 1. And we know that the derivative of negative 5x to the negative 1 is going to become negative 5 times negative 1, which is positive 5, x raised to the negative 2 power, because we have to subtract 1 from that exponent. And then 6 is just a constant. So the derivative of that is 0. Nice. Well, how do we simplify this? Well, so we get y prime is equal to 4x, x to the 1 is just x, and then plus 5 over x squared. This would be our derivative function for our y function listed above. Nice. We were able to use, which one rules did we use? We used the constant rule, we used the constant rule, we used the constant multiple rule, and we used the sum and difference rule. We used all three rules in this equation in addition to our power rule from the last lesson. Nice. All right, let's try that number 2. Number 2, we want to rewrite this so that it is easy to take the derivative of using the power rule. I'm going to rewrite that square root of x as x to the 1/2 power. And then what I'm going to do next is I'm going to rewrite this. I'm going to pull that that third out. It's being divided by 3, so this is the same thing as 1/3 times x to the 6th. It's a little bit easier to see taking the derivative that way than having it x to the 6th over 3. And then I got that plus 2 pi over to the 5th power, so 2 pi raised to the 5th power. Let's take that derivative. So if we take the derivative, we're going to call this y prime. The derivative, we've got 8 times 1/2 x to the negative 1/2 power. And then we've got a minus 1/3 times 6x to the 5th. And then we've got plus the derivative of 2 pi to the 5th. This is a constant, right? There's no variable in this term. Pi is a constant. 2 times pi to the 5th power is just a number, so the derivative of that is going to be equal to 0. Let's simplify this so we can get to a nice answer. 8 times 1/2 is going to be 4, so we've got 4 being divided by x to the 1/2, or the square root of x. Then we've got minus 1/3 times 6, so minus 2. 1/3 times 6 is 2. X to the 5th power, and then we've got that plus 0. So this is going to be 4 divided by the square root of x minus 2x to the 5th power for our derivative of number 2. Next part, horizontal tangent lines. As we said, we're doing sort of a grab bag of different topics today. Horizontal tangent lines. When does a function have a horizontal tangent line? Well, if we think about this, this example function that we've got over here, a horizontal line is going to look like this, right? It's going to be going straight across. So when do we see horizontal tangent lines? In this case, I see one right here that would have a horizontal tangent line, and also right here where I see it would have a horizontal tangent line. Those are places where the slope is equal to 0. So the slope of the function is equal to 0. And so the slope of a horizontal tangent line is 0, true. To find where a function has a horizontal tangent line, we set the derivative equal to 0. So if I wanted to find out where it had a horizontal tangent line, I could take the derivative of this function and then find out where it equals 0, where the output is 0, because that would mean the slope of the original function is 0 there. Number 3, find the x values of any horizontal tangent lines of this. Well, if we take our derivative, this looks like it's set up pretty nicely. F prime of x is going to equal 8x. The derivative of 7x is going to be 7, and then the derivative of negative 13, that's a constant, so that's going to be just 0. So our derivative function here is 8x plus 7, and I want to know when it's equal to 0. So 8x plus 7 equals 0, 8x is equal to negative 7, and x is equal to negative 7 over 8. We would assume that for this function here, that it's going to have a horizontal tangent line when x is equal to negative 7 over 8. Just so you know, this graph is not a graph of this equation. These are unrelated, so I'll just write that, unrelated. They're not the same graph, so don't worry about that. But one thing I will mention about this, which is sort of leading into something we're going to talk about later in our derivative chapters, is notice that for this function, where the horizontal lines are occurring, where are those horizontal tangent lines occurring, they're actually occurring at a maximum and at a minimum. And that's sort of a useful sort of preview that places where functions have maximums or minimums have horizontal tangent lines. Cool. We'll talk about that more when we get to those lessons. Normal lines. All right, so we talked last lesson about parallel lines. And so I want to remind you, parallel lines from sort of like Algebra 1 have the same slope. They have the same slope. And that's useful. A normal line goes through the same point the tangent line does, but it is perpendicular to the tangent line. So normal is the same thing as perpendicular, which was also something you probably talked about back in Algebra 1. The slopes of perpendicular lines, so slopes, have opposite reciprocals. Opposite reciprocals if they're going to be perpendicular to each other. So using some of those fun facts from Algebra 1, if we're going to find the equation of the normal line, then we would need to find something that has an opposite reciprocal of the slope of the line that we're looking at. All right, so we have a graph over here of this function x cubed minus 4x squared plus x plus 3 at x equals 3. If we go to x equals 3, we can see this is the point that we're talking about over here. Now, if I draw here, we can draw our tangent line. Right, this would be our tangent line. But we know that this is asking for the normal line. And so the normal line, again, is going to be perpendicular to that tangent line. So it looks something like this. Maybe not exact, but that red line that I've got here would be my normal line. And sort of the key for this is that the normal line is perpendicular to the tangent line. So I can add those little 90-degree symbols there if I were drawing on this graph to just emphasize that it's perpendicular, it's 90 degrees from that. So if I want to find this equation, well, first off, I would want to know what is the slope of the tangent line. So in this case, if this is our equation, let's take the derivative. F prime of x is going to be equal to 3x squared minus 8x plus 1. And then the derivative of that 3 is going to be 0, so that's it. But what's the slope of the tangent line at x equals 3? Well, let's find out f prime of 3. F prime of 3 is equal to 3 times 3 squared minus 8 times 3 plus 1. So that's going to be equal to 27 minus 24 plus 1. So that looks like it's going to be about 4. So f prime of 3 is equal to 4. Additionally, we're going to want to know what the output of the function is. If we're writing the equation of a line, remember the two things that you need are a point and a slope. We just found the slope. We know that f prime of 3 is equal to 4. So we've got that. That's good. The point, if I want to do that, it means I just need to plug in x equals 3 to my original equation, and I need to find out what f of 3 is. And so that's going to be 3 to the third minus 4 times 3 squared plus 1, not plus 1, plus 3 plus another 3. If we do that, that's going to end up telling us that f of 3 is equal to negative 3 for that. So my point is going to be the point 3 comma negative 3. I got my point, I got my slope, and what we're going to do to finish this problem out is we're going to remember our point slope form. that y minus y1 is equal to m times x minus x1. Remember, point slope form. And I'm going to just plug in. So this is going to be y minus -3 is equal to the slope 4. Ooh, can't forget. So let me step back. If I plug in 4 for the slope of this equation, that would be a parallel line, because this equation I'd be making would have the same slope. So remember, if it's going to be perpendicular, we've got to take the opposite reciprocal. And the opposite reciprocal of 4 would be -1/4. It's a reciprocal because we flipped the fraction, and it's opposite because we changed the sign of it. So the slope here is going to be -1/4 for our normal line, times x minus x1, which is 3. So total, I got y plus 3 is equal to -1/4 times x minus 3 would be my equation of the normal line for number 4. Nice. Number 5, differentiability with piecewise functions. All right, we talked before about functions being continuous or differentiable, those being different things. We know that if a function is differentiable, if it's differentiable, it must be continuous. It must be continuous. And back in chapter 1, we learned how to find out whether a function was continuous. Specifically, we can set both of these parts equal to each other, technically finding that limit from the left and limit from the right, and seeing if they're equal at the given x value. So I'm going to take that 5x squared plus 3x plus 2, and I'm going to set it equal to -7x minus 3. But I care about this when x is equal to -1, because that's where these two parts of this function are meeting each other. So I want to see is the left side equal to the right side. So if I do this, 5 times -1 squared plus 3 times -1 plus 2 is equal to -7 times -1 minus 3. Is this true? 5 minus 3 plus 2 is equal to 7 minus 3. 5 minus 3 is 2, 2 plus 2 is 4, so 4 is equal to 4. Yes, that's true. So this function is continuous. So I will say yes, continuous, based on the work that I just did right here. But is it differentiable? Remember from earlier in this chapter, we said that a function can be continuous, but that doesn't mean it's differentiable, right? An example of a function that might be continuous but not differentiable would be like an absolute value function, where we've got this thing like a cusp there. The way that we can tell that it doesn't have this point or this cusp is that it would need to be smooth, right? We can't have this sort of pointy thing. And the way that we would do that is we can actually set the derivatives equal to each other. So we want to set the derivatives equal to each other. And let's find out if those are the same. So I've done this work over here, but now I'm going to take the derivative of 5x squared plus 3x plus 2. The derivative of 5x squared plus 3x plus 2 is going to be 10x plus 3. And the derivative of -7x minus 3 is just -7. And I care when x is equal to -1. So I'm going to plug that in. 10 times -1 plus 3 is equal to -7. Yeah, it looks like -7 is equal to -7. So yes, this is both continuous and differentiable. Yes, differentiable. And that's my conclusion for this. Pretty limited on space, but we got it to fit. Hopefully you didn't write big for that one. Number 6, this looks like the last one for today. So what values of a and b would make the function f of x equal to this piecewise function differentiable at x equals 3? Remember, if it's differentiable, it needs to be continuous also. So that's sort of a key thing. So if it's going to be continuous, those two parts of the piecewise function need to equal each other when x is equal to 3. So I'm going to say that x squared minus ax plus 2 has to equal x plus b when x is equal to 3. So 9, if we plug in that 3, minus 3x plus 2 has to equal 3 plus whatever b is. If we combine our like terms here, 9 plus 2 is 11, and then if we subtract the 3, that's going to be 8. So 8 minus 3x is equal to whatever b is. And actually, I want to step back. I made a little mistake here. This should be not 3x, but 3a for both of those, because the x was 3. So 3a. So 8 minus 3a is equal to b. I'm going to stop here for the moment, because we've done as much as we can with that. I can't solve for a or b quite yet, but I'm going to move to the differentiable side. So differentiable. Is this thing differentiable, or how do we make it differentiable? In that case, the derivative of each of these things would need to be the same. So the derivative of x squared minus ax plus 2 is going to be 2x minus whatever a is, right? Because a is a constant, and then so the derivative of ax is going to be just a, and the derivative of 2 is a constant, that's going to go away, that's going to be 0. Derivative of x is going to be 1, and the derivative of b is a constant, that's going to go away. So I know that 2x minus a is going to equal 1 when x is equal to 3. So that means that 6 minus a has to equal 1, and that means that a is going to be equal to 5 for that problem. So now that I know what a is, I can go back to that original equation that I had over here, and I can plug in and solve for b. So I know that 8 minus 3 times 5 has to equal our b. So 8 minus 15 is equal to b. That means that b is equal to -7. So I've got my a, I've got my b. Those would need to be the two equations, rather the two values, in order to make this function differentiable when x is equal to 3. That's it for today's notes. Try the practice out, check your answers, stop by either office hours or class time if you've got any questions, and do that mastery check. Have a great rest of your day.